He received his Bhatnagar Award in 2013 and elected to the fellow, became a fellow of Indian Academy of Sciences in 2014 and a fellow of Indian National Science Academy in 2021. So Eknath, please.
Okay, so can you hear me? I have this tricky situation of using the mic in one hand and the pointer in the other. But thank you all for coming. And thank you, Professor Munshi, for the introduction. So this is going to be a post-pandemic talk. In other words, it's going to not be related to anything related to COVID. And it's about pure mathematics. So I've tried to make it very elementary. I hope I can reach out to some of you. Yes? You may want to hold the mic a little lower. Okay. Yeah, sure. Can you hear me now? Is it better? Okay, so the title of the talk is Galois representations. Can you see? Okay, so Galois representations. Let me start with Galois theory because this is probably where many people probably stopped doing mathematics. I can only count a few mathematicians here, so I'm addressing the people mostly in this audience who are not mathematicians. But Galois theory is maybe some advanced topic in undergraduate or master's level where people stop doing. So let me quickly recall Galois theory in one slide, and then we'll take it up from there. So what is Galois theory? So we all know this famous quadratic equation. So this is going to go back and forth. I hope the sound is not too erratic. So ax squared plus bx plus c equals 0. Famous quadratic equation. When we were in class 8 in schools in India, we learned this formula. X equals minus b plus minus square root of b squared minus 4ac all over 2a. There's some competitions about how fast you can say that formula when you're in school. But the point of this formula is that you are solving this equation by radicals. There's some square root signs. So a natural question arises, and that is, when can you solve a polynomial equation like this by radicals? And the answer is surprisingly both intricate and simple at the same time. So this was an answer given by Galois. I'm not going to show too many photographs in this slide. I could have, but I decided not to. So there's something called a Galois group attached to a polynomial. It's a finite set with some operation on it, the way to combine two elements of the set to get a third operation, to get a third element of the set. So you would need that this group should be what is called a solvable group, which is a good word because solvable equation is solvable if and only if the group is solvable. So here's an example. If you try and solve that by these square roots or cube roots or fourth roots or fifth roots, you won't be able to solve this equation because the Galois group of this polynomial is, it's not important what this group is, it's some group of order 60, it has 60 elements in it. The group is A5. It's not a solvable group. Okay, so now I want to introduce the Galois group. This was the Galois group of polynomial. That's a finite group, but there's some the Galois group, which is a big infinite group, which contains the information of all these finite Galois groups attached to each polynomial. So let Q bar be the field of all algebraic numbers. So you take the rational numbers, all fractions, and you tack on root 2, cube root of 5, square root of minus 1, things like that. You get the field of algebraic numbers, and you let G be the Galois group of Q bar over Q, which means that you look at all automorphisms of the big field, Q bar, which pointwise fix Q downstairs. So note that if you have a root of a polynomial defined over the rational numbers, then, and sigma is one of these automorphisms, then sigma of alpha will be another root of the polynomial if alpha is a root. So for example, if you have the polynomial x squared equals 2022, the roots are plus minus square root of 2022, and sigma will take one of those roots to the other, or maybe just fix it. Can't do anything else. So this group G, which I mentioned above, looks a bit abstract, but you should think of it as containing information about the Galois groups of all polynomials. Okay, so all these finite groups that I was referring to earlier are quotients, sort of images of this big group. And a somewhat mysterious group, and maybe maybe this is a slightly facetious sentence, but one can say that at least algebraic number theory is concerned in studying this mysterious group G. Okay, so when you try to study a group G, it's sometimes a bit difficult. So we adopt the viewpoint of what physicists do. They look at shadows of this group, shadows in the sense of representations. You look at images of these groups on matrices. So more formally, you have some homomorphism from G to GLNA. So GLNA is just n by n matrices, which are invertible. A is some ring. It could be, it's going to wind up being some p-adic ring, but just think of it as some field or some ring right now. For example, you could think of the complex numbers, but in this talk, it won't be the complex numbers. So these maps are called Galois representations. And the one-dimensional Galois representations are completely classified by what is called class field theory. And this is something that you study if you're in your second year or third year of graduate school and you're doing algebraic number theory, you'd read a book on class field theory. It's like studying linear algebra and number theory. It's a basic thing that people study. Most things are known, but there are some open problems still here. Okay, so what about higher dimensional Galois representations? That was the case n equals 1. Well, a large class of Galois representations for n equals 2 come from what are called modular forms. Because the modular forms are very classical objects. They're complex valued functions on the upper half plane with many symmetries. And the important thing about them is that they have a Taylor expansion. So they can be written as, some people call this a Fourier expansion, which is not completely right. But you can write such a function as summation a n q to the n, where q is equal to e to the 2 pi I z. Z is in the complex upper half plane, function on the upper half plane. And modular forms have a weight, k, which is an integer greater than or equal to 2, and they have a level, n greater than or equal to 1. I'm not going to define those in a lot of detail. Just remember that Galois representations come from modular forms, and modular forms have a weight and a level. So there are two parameters that you can attach to any particular modular form. So as I was saying, for each modular form, for each nice modular form, so there are many words here that I'm skipping, what nice means. But for each nice modular form, let's say a weight k greater than or equal to 2, there is a two-dimensional Galois representation, rho f, from the Galois group of Q, G, to GL2A, where A is some p-adic ring. You can think of it as the integers, but it's actually the p-adic integers. And actually, that's just one example. It's actually some finite extension of the p-adic integers, but it's not important here. So just to summarize so far, the Galois group of Q is a very mysterious group. We study it by its representations. One-dimensional representations are given by class field theory, and two-dimensional representations, and a large class of them, are given by modular forms. In some sense, all Galois representations should come from modular forms, but we won't get into that. All two-dimensional ones, and even maybe n-dimensional ones. So here's an example of a modular form. The first one, perhaps, because it has level 1, where the weight is 12. If you want the weight to be 2, then this is not the first modular form. The first one has level 11, but okay, it depends on how you count. So this is the famous Ramanujan delta function, which people may have heard about. I sometimes give public lectures just on this particular function. There are many beautiful things you can say about it. Let me just say one thing here, that these coefficients, which are the Fourier coefficients here, these a-n's, which are the tau n's now, the special notation because it's a special function. These numbers, which are actually integers, were extensively studied by Ramanujan. And let me just, as a running example, mention that the fifth Fourier coefficient, tau 5, which is 4830, is 5 times 966. Yes, there's a question. What was? k is the weight of the modular form, and n is the level. So in these functions have some symmetries, and in these symmetries, these numbers appear, k and n. So if you're interested in a bit more detail, then f of az plus b over cz plus d, that's the Mobius transform of some element z in the upper half plane, is actually equal to cz plus d to the k times f of z. That's the functional equation that these things satisfy, and the k shows up in that equation. So the weight is 12 here. So let's look at the fifth Fourier coefficient, and I want to emphasize that 5 exactly divides that number. Okay, so this talk is not about the actual Galois representations attached to modular forms. I'm going to restrict these Galois representations to the domain. I'm going to restrict the domain a little bit to what is called the local Galois group. Okay, so there's a technical word for it called the decomposition subgroup. But you should think of at each prime number p, there's a special subgroup which is called the decomposition subgroup at p. It's actually the Galois group of the p-adic numbers. So let's restrict the Galois representation from G to GP. Okay, so now we have, instead of a global Galois representation, we have a local Galois representation. And I'm going to do one more thing. I'm going to actually also mess with the range a little bit. So I restricted the domain from G to GP. I'm going to also mess with the range a little bit. So remember, these are matrices in GL2 of Z or something like that. But I'm going to go modulo that prime. I'm going to go into GL2 Z mod P. So each of the entries of the matrices, I'm going to reduce mod P. Okay, so these are representations into GL2 of a field, a finite field with P elements, let's say, or Q elements, where Q is a power of P. So you have these homomorphisms. Okay, so here's the basic question that I've been looking at for the last 7 years. So one wants to know whether these representations are big or small. So small in the sense that you have these 2 by 2 matrices. Sometimes you only get diagonal matrices. So in those cases, you say that the representation is reducible. Sometimes you get upper triangular matrices with a 0 in the bottom left corner. This is still reducible. And sometimes you get basically all the entries are there, and you get something what is called irreducible. So you can think of irreducible. They have some formal meanings, of course, but reducible you should think of with some zeros appearing in the matrices, and irreducible with no zeros. So let's do an example. So for example, if you go to the Galois representation attached to the delta function of Ramanujan, so you take f to be delta, and you take the prime p to be 5, then this reduction rho bar has 2 zeros in the anti-diagonals. Okay, that omega squared and omega are not important. There's some characters. But you have some zeros showing up in the matrices. You always get diagonal matrices, and so this particular representation is reducible. I'd like to quote some Indian mathematicians and not always foreign mathematicians. So at the beginning, I quoted Ramanujan. Let me also quote somebody from Punjab University, Bamba, who proved this beautiful congruence, even mod 25, I think, a long time ago, maybe in the 30s. And so I want to explain this notation, but it follows immediately from that congruence. So just to reiterate, that's the question. Is the Galois representation reducible or irreducible? And here I'm saying for P a good prime number. What does good mean? Well, the level was 1 there, so all primes were good. But sometimes there's a level, and so you want your prime to be away from this integer n. You want P not to divide n. So good primes have nothing to do with the level of the modular form. Okay, so what is known? So the answer seems to depend essentially on 2 quantities. One is the weight of the form, which is a positive integer greater than or equal to 2, as I've mentioned many times already. And gentlemen asked me the definition, and I gave it. And the other is, there's this pth Fourier coefficient, like tau of 5 was 5 times 966. So it seems to depend on how divisible that particular number is by p. Okay, so that's what's called the slope. So actually it's not just an integer, positive integer, it's a non-negative rational number in general. which measures how divisible AP is by P. And let me just give that example again. Remember, when we had the delta function and P was 5, 5 divided that number exactly once, because 5 didn't divide 966, the other part. So the slope was exactly 1. So somehow the answer seems to depend on the weight of the modular form and the slope. Okay, and in most cases. And here is some known results. For small weights, it was complete. For very small weights, the Galois representation is always irreducible. But if you up to weight P plus 1, but if you go up to weight 2P plus 1, then it can become reducible or reducible. But anyway, everything is completely known for small weights. It's also known, I wanted to make this talk not a summary talk of thousands of results, so this is my only sort of slide with lots of results on it. Rest of the talk will focus on just one result, which I'll come to in a second. It's also known for large slopes, if V is bigger than the floor of K minus 2 over P minus 1, etc. Remember, V was the slope. I wish this pointer was working, but it's in point 2 there. It's how divisible your Pth Fourier coefficient is by P. So you can think of it just as an integer, but in general, it's a rational number. It's also known for some small slopes. For V equals 0 by Deligne, for example, P doesn't divide AP at all. The answer is very easy in that case. It's known for slopes essentially up to slope 2 by various people here. Completely known in these cases. Okay, so what do I want to do today? I want to go back to this running example. So if you look at the delta function and P equals 5, then notice something, a nice congruence. So the weight is 12, and 12 turns out to be, this looks like a very strange thing to say, but it's important for the talk. 12 is 2 more than twice the slope modulo P minus 1. So what is twice the slope? Twice the slope was 2. 2 more than that is 4. So 12 minus 4, which is 8, is divisible by P minus 1. In this case, P is 5, so that's true. Okay, so I just want to make this remark that this particular example satisfies the property that the weight is congruent to 2V plus 2 modulo P minus 1. So let us say that a weight is exceptional if you have this relation between the weight and the slope. So it turns out that exceptional weights are very tricky to treat. The answer doesn't completely only depend on the weight and the slope. It seems to depend on something more. Because when you have exceptional weights, the Galois representation has some reducible answers and some irreducible answers. So there's something delicate going on here. So let me make a conjecture about what I thought was happening. So this appeared in print just last year in a Japanese conference proceedings, but it was sort of in the air for about 4 years before. The pandemic, this volume took some time to come out, but it was on the archive already in 2019, and maybe I gave some talks about it in 2018 already. So my conjecture is the following, that if you have a half integral slope, notice that the slope was an integer before, but in some cases you can also get half integers, and it's allowed to be reasonably big. It's allowed to go up to P minus 1 over 2, not just small slopes, but allowed to go up to P minus 1 over 2. And suppose that your weight is exceptional with respect to V. In other words, the weight is congruent to 2V plus 2. Remember, 2V is now an integer because V was a half integer. So 2V plus 2 is really an integer. And the difference, K, between K and 2V plus 2 should be divisible by P minus 1. So suppose that holds. Then the claim is that the Galois representation mod P, the local Galois representation mod P, the thing we're trying to study, is not just reducible or irreducible, but in fact it varies through an alternating sequence of irreducible and reducible representations. Depending on the size of two new parameters, which I also had conjectured, the exact shape of these parameters, which I'll come to in a second. So it's not just the weight K and the slope V, but in addition, there are 2 more parameters, tau and T. And depending on the positions of tau and T on the rational line, you get a reducible or reducible answer. And you get some sort of zigzag pattern. So I call this the zigzag conjecture. So more precisely, let R naught be twice the slope. Remember, V was a half integer, so 2V is just an integer, so R naught is an integer. Then, if you draw this tau line here, you can point to this at least, tau, then you have these numbers t, t plus 1, that's the other parameter. You go all the way up to this integer, t plus n, where n is R naught minus 1 over 2, or R naught minus 2 over 2, depending on R naught odd or even. There's finitely many integer points. T is an integer, but tau is a rational number. Turns out that in the left interval, you get something irreducible. At this integer point, you get something reducible. Again, in this fractional range between t and t plus 1, you get something irreducible, reducible. And it alternates in this way, reducible. And finally, it ends with either a reducible or an irreducible answer, depending on whether your R naught is odd or even. Okay, so this is the conjecture. So the summary of this is that you're trying to compute the mod P reduction of these local Galois representations and discover whether the image is large or small. Small means there's some zeros appearing in those matrices. Large means mostly there are no zeros in the matrices. And both cases happen, and they seem to happen in this strange way, alternating sequence of irreducible and reducible cases. Okay, so let me quickly define what these parameters tau and t were. They were a bit mysterious because tau was that line and t were these numbers. So some more notation, let R be the weight minus 2 and R naught be K naught minus 2. So actually R naught was defined on the previous slide. So maybe I should have written that as K naught is R naught plus 2 because that defines K naught. But anyway, for symmetry, let's write it like that. So tau is the following strange number. It's not a slope, it's a kind of a slope, but it's a slope of a more complicated quantity. So I'm looking at how divisible a certain fraction is by p. And what is this fraction? Well, it involves the pth Fourier coefficient, ap squared, but it also involves some binomial coefficients, n choose m, where n choose m are those numbers. There are two binomial coefficients, r minus v minus choose v plus, and r minus v plus choose v minus, times p to the r naught. And then you divide the whole thing by p over ap. Okay, so this is some slightly more complicated number coming from the modular form than just AP. Some quadratic expression in AP on the top and some linear, P times a linear expression in AP on the bottom. You divide the two. You get some number in some p-adic field, and the valuation, how divisible P is, how divisible this number is by P is that VP thing. You get some rational number. And what are V minus and V plus? These are, so remember V was a half integer, so every half integer lives in some, has some endpoints, lives in some V minus, V plus, some integer. So V minus is the largest thing and V plus is the smallest integer such that V belongs to V minus V plus. Okay, so I told you the parameter tau first because it's a bit more complicated but very explicit. And here is the parameter t. It's just the valuation of k minus k naught. So now you have complete information about the conjecture. Okay, so how did one arrive at this conjecture? So in our investigation of this conjecture for small slopes, small half-integral slopes, so in fact, the case for v equals half was done by Buzzard and Ghate. It's in the range 0 to 1, way before I started looking at this problem. But we did something for slope 1 and slope 1.5, where the p-adic valuation of v of AP is 1 and 1.5 in those cases, because those are in the range of slopes up to 2, and we noticed that this kind of pattern was coming, and so based on that, we could prove the conjecture, and the proof uses some very beautiful generalization of class field theory to the two-dimensional world called the Langlands correspondences. So this is a very explicit version of the Langlands correspondences, almost for computer science. It's like a mod P local Langlands correspondence. Everything can be written down completely explicitly. It's discovered by Breuil. But so the first paper there is 10 pages, the next one is 40 pages, and the last one, still a preprint, is 70, 80 pages. So this was quickly blowing up the size of the arguments one had to give in the proof. So today I would like to state the following theorem, which was posted on the archive 3 weeks ago, or 4 weeks ago. So as I said, I just want to talk about one result today, and this is the result. So I'm claiming that in fact the zigzag conjecture holds more generally, not all the way up to p minus 1 over 2, but for slopes up to p minus 3 over 2. So the top two slopes one has to avoid. So there's the reference. So you can see it's November 22. And as I said, we avoid the top two slopes. So one technical remark is that in the zigzag conjecture, the conjecture was true if t was sufficiently large. But actually in these three special cases, you don't need t to be sufficiently large. T can be 0 also. Okay, but when we prove it, we do need that t is sufficiently large. In fact, there are counterexamples already for slope 2 for small values of t. So you do need that t is sufficiently large. Any questions? I'm doing okay on time, so I can pause finally. Yeah. Sorry? Yeah. I sort of naively made this conjecture for those two values as well, but I'll explain why we exclude them at the end. Turns out we use some results in the literature for which something is not true at these 2 points. So that's more like a sort of, since we're using other people's work who haven't said something in these cases, we can't conclude something for our conjecture. Might be forced to revise it, but I'm old enough not to lose my job, I think, if it's wrong. But yeah, I said it was essentially, let me just say it's essentially correct, this theorem. Any other questions? Okay. So let me now go from the proof. The proof, sometimes when you work in algebraic number theory, there are lots of sort of algebra, and that's all there is. But the nice thing about this proof, it uses some geometry. So I thought I'd sketch the proof. And it uses a construction in geometry called blowing up, which is something that I had to watch many YouTube videos about before I fully understood it. You can also do that. There's some very nice videos about blowing up the plane at a point. What that actually means, I'll try and describe it here. But it has something to do with blowing up. Okay, so let me first give the very rough idea of the proof and then give more details. So what's the rough idea? The rough idea is that you use a limiting argument to change from the case of a good prime to the case of a bad prime. So I'll define what bad prime is soon. And the second part of the argument is to then use results in the literature for the case of bad primes. Okay, so we were studying the reductions, local reductions of Galois representations at good primes, but somehow we want to reduce to the case of a bad prime and then use work in the literature for where things apparently are known. So what is good? Well, good, so now I'll use for the first time some technical words. So good means that this particular Galois representation, not the reduction, but the one in characteristic 0, the one from the Galois group of QP to GL2 of Z or ZP or something like that, not into the finite field. This representation is crystalline. So this word I'm just going to throw out there as a black box. But it means that, that this representation rho is a very well-recognized representation, which depends on two parameters, K and AP. It's a crystalline representation with some weight K and some parameter AP. The same AP, which is the AP in the pth Fourier coefficient of the modular form, and the same weight K. K is the weight of the form. And bad means, so bad happens actually when P divides the level. Okay? Actually, P exactly divides the level, and AP The pth coefficient is, in this case, turns out to be plus or minus this number, but I restricted the case p to the plus sign, p to the k minus 2 over 2. In that case, it turns out that the characteristic zero representation is not crystalline, but what is called semi-stable. It's of the form VKL, where K is the weight of the form and L is a new parameter, which parameterizes semi-stable representations called the L invariant. Okay, so I'm now going to drop this sort of naive language of good and bad and work with crystalline representations, which are good prime representations, and semi-stable, which are bad prime representations, even though I want to study only the good prime ones. Okay, so here's the first limiting result, the part 1 of that sketch of proof I did, and then part 2. So now assume that your AP is not just a fixed number. Suppose that AP varies in a family, because you want to take some limits. So suppose that AP is a function of the weight K. Remember, you have this VKAP. So we want AP to be a function of K. And suppose that it's a smooth function. Smooth here means differentiable once, even differentiable twice. But you can even assume, if you don't like that, just differentiable infinitely often. So it's a function of K, but you're restricting to all K's congruent to a fixed K naught. That K naught came up earlier. It was basically 2V plus 2 modulo P minus 1. And assume that this function at K naught, it's a function of in a neighborhood of K naught, so you can talk about its value at K naught also. Suppose that it's exactly this, P to the R naught by 2. Okay, then we have the following limiting result. It turns out that as K approaches K naught p-adically, that means the difference gets closer and closer, gets more and more divisible by a high power of P, more and more divisible by powers of P. Then, as K tends to K naught, this particular crystalline representation converges to that particular semi-stable representation. So what is happening here? So suddenly you have to change your viewpoint, and you think of each of these Galois representations as points in some parameter space, some moduli space of Galois representations. So it's some geometric space which is somehow classifying Galois representations. The crystalline representations are certain points in there. The semi-stable representation is another point in there. And as K tends to K naught, these actual dots, these Galois representations are converging to that bad Galois representation. Okay, so the first ones are crystalline because they're of the form KAP. The second ones are semi-stable, K naught L. And the star there is some dual representation, which is not important, but technically speaking, you have to put it there. What is L? You can even give a formula for L. L is basically the derivative. It's the rate of approach of it's the tangent direction of AP at K naught. More precisely, the logarithmic derivative, but there's a factor of 2 also. Okay, so these semi-stable representations are converging to this, crystalline representations are converging to this semi-stable representation, and you can even predict the L invariant in terms of some tangent direction. So now when you have these Galois representations converging to this semi-stable Galois representation, it turns out that the reductions after a while all become constant. So they all become, because if the limiting thing is reducible, then as you get closer and closer to it, the mod P reductions also become reducible. If the limiting thing is irreducible, no zeros in the matrices, then the limiting things also, eventually the mod P reductions are irreducible. So this is why this result is important. At least in a neighborhood of the semi-stable representations, you can hope to study the conjecture if you know the behavior of the reductions of semi-stable representations. So this is an older paper from last year. It's also on the archive with student Chitrao and a Japanese gentleman, Yasuda. Okay, so how do we prove this? This is where I was talking about blow-ups. So both these representations live in a larger class, a larger world of representations called trianguline representations. And the convergence takes place in a certain blow-up space, which is a parameter space for trianguline representations. Okay, let me give a proof by picture of that previous theorem, which will motivate the proof without giving a proof. It was a colloquium talk at a university. I'd actually spent 15 minutes on the proof. But here, let me give a proof by picture. What is this blow-up stuff? So you have the plane. Let's just do this over the real numbers. Go back to functions in class 8, 9, 10, etc. So you have the plane xy belonging to R2. The blow-up is this space. You attach some projective coordinates, a colon b. Okay? And you have this relation that xb has to be equal to ya. That's the formal definition of the blowing up of the plane at a point. Okay, so notice what happens. If you take x and y both to be 0, 0, that equation is pretty silly because every a and b will satisfy 0 times b is equal to 0 times a, right? So at above the point 0, 0, you will have lots of points, a whole p1 worth of points. Whereas if x and y are not zeros, then the ratio p to a is kind of determined by y over x. It's pretty rigid at the other points. Okay, so what the blow-up is doing is that at each point outside the origin, you have a unique point upstairs, and at the origin, you have a whole p1 worth of points. Okay, so here is what I just said. For most of the plane, so the x-axis is there, the y-axis is going into the boards because I want a three-dimensional thing, so I've drawn it like that. So at the origin, you have a whole z-axis worth of points lying above that particular point. Moreover, if you take a curve downstairs, y equals f of x, you can ask, what is the lift of this curve to the blow-up? So it lifts to some curve, but it doesn't pass to the origin anymore. So this is the weird thing about blow-ups. When you look at the pre-image of this curve, the usual curve in class 8, 9, 10, you look at the lift upstairs in the blow-up, it goes through that black dot upstairs, but that's not x, y, z equals 0, 0, 0. What is that point? Well, we know that b over a has to be y over x by this equation. So in this particular case, it will be f of x over x. And you can see as x gets closer and closer to 0, that's just taking a derivative, right? So b over a is basically just the derivative. So when you lift that curve to the blow-up, you pass at the height at which you pass is the derivative. And that's what's underlying this proof, that in this world of triangulation representations, you had lots of crystalline representations. The crystalline representations are approaching a semi-stable representation, but they're not approaching the point downstairs. They're approaching, it's a blow-up space, so when you look at the thing that it's approaching upstairs, it approaches basically some tangent direction. Okay, so that's a proof by picture. And so now using this, I can prove zigzag quite easily using that theorem. So first of all, note that as k tends to k naught, the APKs, which are families of APs, they all have the same valuation as AP of k naught. The limit AP, which is R naught by 2, that was the power of p dividing p to the R naught by 2, it was R naught by 2. So in particular, these representations are all exceptional, just to show you that we're working in the framework of the conjecture, because twice that thing is R naught, which is the right thing, 2v. We prove it satisfies zigzag. So let's do some, I'm going to do this computation very fast. So you read the Taylor expansion of AP, that's that, and use that formula for AP prime in terms of the L invariant, you substitute that. So you get that. Similarly, if you try and compute these binomial, we have to compute this parameter tau in t, right? So I'm computing each of these quantities. If you compute this first binomial coefficient, turns out that since these squeezing points, v minus and v plus, are basically R naught, which is k naught minus pi 2, some of them is R naught, you can compute these binomial coefficients and they have this kind of expansion. H plus is the partial harmonic sum with respect to v plus. So 1 plus half plus 1/3 up to 1 over v plus. And similarly, you can compute the other binomial sum. And if you now try and compute this parameter, you substitute all that into this parameter, all these expansions, and do a little bit of algebra, you can see that you get an R naught by 2, that's the third last line here, R naught by 2 because there's a p to the R naught coming out in R naught, but on the bottom you have a 1 and an R naught by 2. So the R naught becomes an R naught by 2 and then minus 1 because of the p in the bottom. And then the 1's cancel in the top and you get this expression nu, which is the valuation of the L invariant minus the harmonic sums. And you get t because of the k minus k naught. So this particular parameter became, one minute. This particular parameter becomes this very simple expression, r naught over 2 minus 1 plus nu minus t. So notice that both tau and t are appearing in that expression. And remember, the relative differences of tau and t should control what happens for the representation, whether it's irreducible or reducible. So this is the last slide. So VKAP satisfies zigzag if and only if you change language into this parameter, nu. So nu is not v, okay? There's a script nu at the bottom, and then the third last line. So it's the valuation of L minus H minus H plus. So if you look at the new line instead of the tau line, and just get rid of the tau and t's, change some variables, then that local crystalline representation, the reduction of it, is given by the zigzag picture if and only if nu varies through this range of numbers, 1 minus r naught by 2. As you vary through this range of numbers, you get, just rephrasing the conjecture in terms of this new notation. Okay, but by the limiting theorem, the reduction of the crystalline representation is the same as the reduction of the semi-stable representation, because it's limiting to it. So therefore, you need the bad Galois representation to have this reduction. And this was exactly what was proved recently by Weber-Park for odd k-naughts, and by Broy-Mazard some time ago for even k-naughts. And this is where that technical issue comes in. They only do it for L less than P and not less than equal to P. P is an odd prime, let's say. Whereas Broy-Mazard also avoid P plus 1 right at the top. So for that reason, we have to. Okay, so I forgot to put a thank you slide, I think. So that's my last slide.
Thank you. Thank you, Professor Ghate. So we have time for a couple of questions. Have any? So maybe I'll ask one. So what is that number AP square minus that? So do you have any interpretation?
No, it's just something that came up with more and more computation. Yeah, it's really nice. Do you see it in analytic number gates somewhere? That expression?
No, not really, but yeah, it looks like something minus the expected value by, so it's kind of a variation of something.
Somehow like that point, those binomial coefficients times p to the r naught is a bad point. AP squared, that's exactly equal to that point, and something really bad happens at the tau is so we're on the right. Yeah, it's some new number, new invariant coming up from modular form. So maybe it's that thing.
Okay.
It's like saying, what is zeta 3? Can you recognize
Oh,
it?
yeah, please. Mike.
It's like saying, what is zeta 3? Can you recognize it? And let me just say it's a new constant of the universe. So, yeah. So, it's some new expression that seems to be coming up in this. But maybe it has some meaning. I'd be very interested why it's quadratic, for instance.
The other thing that I wanted to ask whether, is this whole business of Galois representation, so did it really start with Ramanujan's conjecture about congruences?
Yeah, that's a good question. Yeah, I think essentially that's true. Ramanujan proved many congruences, but many other people did. And Sayre and Swinnerton and Dyer, I think you know this question, but it's for the answer, but it's for the audience. Yeah, Sayre and Swinnerton and Dyer then wrote some papers using Galois representations to study some of these congruences. So almost every congruence that you have in number theory, you can write down in terms of Galois representations. So for example, the famous one about the delta function being congruent, tau of n being congruent to sigma 11n. That's just the delta function is congruent to an Eisenstein series mod 691. And the one that I had in this talk was that the delta function was congruent to the theta operator attached to the weight 2 Eisenstein series mod 5, because there was an n times tau 1n, some theta operator. It differentiated.
Okay,
so the Galois representations are the same mod p.
So any other questions? Okay, so if not, let's thank the speaker again. Thank you.
Thank you very much.